Okay, I'm going to start again. So I've shown you for the low energy neutrinos, first all the work that was done with the sun, and now the impressive work that's being done with nuclear reactors, which has basically now changed the research being done for the very low energy neutrinos. We no longer use the sun to do that because we're limited in the number and what we know about them. And instead it's nuclear reactors. And I showed you what has been done, which is impressive already. I'll give you a glimpse of the fact that there's ambitious plans actually underway to do even more for reactors for the future. And that's being done in China. So the Chinese have the most ambitious plans to pursue neutrinos from nuclear reactors. The new experiment, the one they did, was what I call Diabei, which was the best of the present reactor experiments. The new one is a different one. It's in the same rough region of China, but it's totally separate. And it's called Juno. So someday you'll read about Juno. It's just being started to be built, excavating in a mountain where it's being built, and they're starting to build the detectors. This should be operational in 3 years from now, something like that. And it has some specific goals, and I'm going to show you how it works before I go on to high energy accelerators making neutrinos. So the reaction that they want to study from reactors is shown here. It's an anti-electron neutrino. That's what comes out from the fusion process in a reactor, interacting with protons in their detector itself, and that makes a positron and a neutron. These three together, if you turn this around, is just beta decay. So just like what was first seen in beta decay, or this is also the same reaction that can be seen with neutrinos from the sun. They've then designed an experiment to analyze these neutrinos as well as they can. That is, let them scatter off a proton like this. This is them coming in, scatter off a proton. It makes then a positron and a neutron. And they've made a special device that can detect these neutrons. So the neutrons move along and they stop, and eventually they give a delayed signal of a photon that comes off in the way they're captured of 2.2 MeV. This is a unique signature. The positron also comes off, and it interacts with the material of the detector to give two photons. They're known energy, and they go off opposite to each other, 511 keV. So this is a total distinctive signature. It doesn't come from anything else, and this should allow them or enable them to do really precise measurements of neutrinos. The first question, and maybe the one that they hope to answer, is one that I've mentioned several times, and that is that they want to be able to tell for sure what is the mass ordering, what we call the mass hierarchy. Which one is the lowest mass neutrino, which is the second, which is the third. As I said, there's an ambiguity with everything that we know now, and the consequences are very different. So the physics cares what is the ordering of the neutrinos, so we have to find out. What they show here is that they've designed this apparatus that can tell the high probability. 5 sigma means that the probability of getting a wrong answer is less than 1 every 100,000 times that you did the experiment. So you're very confident afterwards. But it'll take about 6 years of data taking, another few years to build it. And so we're talking about 10 years from now. But I'm telling you what is being done. So that's Juno. This is the features. It's optimized to be exactly the right distance where you can measure these parameters. So from the nuclear reactor, they calculate that they want to be 53 kilometers away. I'll show you that's what they've decided. And they need energy resolution to be able to make sure that they can do this. It's written here, 3% over the square root of E. They need all these other features, which I'll just list because I'm not going to go through all this stuff in detail. They need a source that's really powerful. Where they've picked is a place where in China, much of the power comes from these power reactors. They're very powerful ones, and there's 10 of them within this 50-kilometer distance. They decided that the experiment, rather than the present ones, would be much quieter if they buried it underground. So they're buried 700 meters under the surface of the Earth. And I just give an indication here that at that depth, there's about 3 cosmic rays, what we call muons, that penetrate per second. That's a rate that's about 1/10,000th of what it is on the Earth's surface. So it's a very quiet environment. The energy resolution I gave, and then they do a tremendous amount of work in what they've designed to make sure that the systematic errors are very small. So this is where it is. And you can see that Juno itself is in a mountain, 53 kilometers away from 2 nuclear reactor centers near Daya Bay, but nearer Hong Kong. Hong Kong's over here somewhere. So it's just in China from Hong Kong. This is what the devices look like. They look a little bit like the detectors I showed you in Canada, a sphere, where the sphere is full of the detector element. That's a liquid scintillator. I think each one is about 20 kilotons of liquid scintillator, and surrounded by water that absorbs the background. That's what they call the Vito pool. So that's the detectors. And it can detect neutrinos that come from the collapse of a star. They can detect neutrinos that come, as I mentioned earlier, from the core of the Earth. So within a decade, you'll be reading about what we know about the core of the Earth, and it's going to come from neutrinos. Neutrinos from the sun, and of course neutrinos that come from nuclear reactors. These I'm just going to flash at you because of time, but they're in my notes. They're in the slides that'll be posted. So they basically can demonstrate from their calculations that they can measure all these different kinds of neutrinos. For example, this is the burst of neutrinos that came from a supernova. And this is their ability to do that, even depending on what the supernova signal looks like. These signals from a supernova have never been observed. So this is new. We know what happens when a star burns, but the neutrinos that come from a supernova come from a different mechanism. When a star is burning, the core has a fusion process. When a star burns up too much fuel, then the outward pressure from the fusion reaction, which was balanced by gravity trying to pull it in, loses. Gravity makes it collapse. That's what a supernova is. And it makes a bright flash in the sky. That's why they call it a supernova. But it emits also gravitational waves, which I'll talk about in a month, but also a burst of neutrinos that come from the nuclear reactions that happen when this collapses into a very dense core. So this is a tool then that will be used to understand really what happens when stars collapse or explode. And they've designed to do that. This shows their ability to, and you can look at the slides to see this, I just don't have time to go through all these numbers. This is for geoneutrinos, that they'll actually be able to use this to study the neutrinos that come from deep down in the Earth. And for the first time, we have a probe that can go deep into the Earth and tell us what the core's like, the mantle's like, what happens what kind of reactions happen, what materials are there, and so forth and so on. So basically that's those reactors. And from a standpoint of most of what I've been talking about here, they want to measure accurately the mixing of the neutrinos. The hope is that this experiment will be good enough. We've already, that once we determine the parameters, that they can see whether there's what's called CP violation. This is what I call the mirror symmetry. When I talk, maybe for the last lecture of this course, I'll tell you what we know about, or think we know, about how to explain why we have a matter-dominated universe. As I've mentioned many times here, everything we do react in physics with particles makes an equal amount of mass and matter and antimatter. So the simplest picture of the Big Bang would be that you created a lot of energy in the Big Bang. It's supposed to create matter by Einstein's equations. But when it creates matter, there should have been as much antimatter as matter. It's all close together. It would annihilate. And so we would never be able to put it together to make galaxies and planets and us and so forth. So there's an asymmetry that was there in the Big Bang that we don't understand. And we need to find the clues for that. We do understand some mechanisms that could possibly make an asymmetry in the early universe. And one of those is the fact that there may be not exact symmetry in nature for neutrinos. And that's called CP violation. We don't know if it's true, but there's a motivation to see if it's true. That requires this very, very accurate experiment. So this experiment will do maybe the ordering of the neutrino masses, we think so, and then finally, hopefully, maybe to tell us whether neutrinos have this asymmetry in nature that can help us explain why we have a matter-dominated universe. So that's reactor neutrinos. The rest of the time today, I want to talk about the other man-made neutrinos, which is also being pursued quite vigorously. And these two methods are how this subject will be done in the future. So one is with reactors, the other is with particle accelerators. The scales become very different. Particle accelerators have particles of very high energy, so you have to go a lot longer in distance for them to change their identity and pursue the question. The first place where it was looked at and done is in Japan. And it was done and is being done and pursued in what's called Super Kamiokande. That's the same detector that I showed you that's being used to do, that was used to do neutrinos from the sun. Instead of using it to do neutrinos from the sun, they're pointing a beam of neutrinos from the other side of Japan, made in a particle accelerator over here, and pointing it so that some of them go through this detector and become detected. And they've been able to do that. So that was basically the first one. And it was done just like the experiments on the reactors. This is just a picture of that same big detector where I showed you that they looked for proton decay and then they saw neutrinos from the sun and they imaged neutrinos from the sun. In the same way for the high energy neutrinos, because of a phenomenon called Cherenkov radiation, if the high energy neutrinos make something that goes through the apparatus, they actually make a ring of radiation. So rather than seeing the sun as an image, you're using the same technique in this apparatus, you see a ring from the accelerator. And the ring, the center of the ring, the symmetry of the ring, should point back to where the source was, which it does. And this is the picture then of the detection of man-made neutrinos from an accelerator rather than the ones from the sun, coming into this same big detector, which we call Super Kamiokande. So that's been done, and from that, they've been able to actually see that the accelerated neutrinos that are made on one side of Japan, by the time they get to the other side, by neutrino oscillations, the right number are there that is consistent with the parameters we had before for neutrinos oscillating and losing or disappearing. So in this case, you start with neutrinos, which are the muon type neutrinos, not the electron type, but the muon type neutrinos made in an accelerator, because they come from the decay of pi mesons or k mesons, and they give muon type neutrinos. And by the time they cross Japan, the number that's expected is the number they see. So when you look at that ring and count how many events they should have seen, using the parameters that were gotten from the neutrino experiments from the sun, they expected 158 events and saw 112, which is consistent, but not exactly the same. And from that, they measure the same parameters that we talk about, these parameters, and the parameters are the ones that determine this oscillation. So this is just the parameters. It's determined in this experiment. And this experiment confirmed that neutrino oscillations don't just happen for neutrinos from the sun, but they happen the same way as the neutrinos that came from the atmosphere, where cosmic rays interact in the atmosphere, and I showed you that one last time. They're more equivalent to these neutrinos, and this result is consistent with that. So we now, again, can have a man-made source to make neutrinos to pursue this subject better. This is just the limits that are gotten using this technique for this experiment. So that experiment, which has already been done, was the first to detect accelerator-produced neutrinos, and over a long distance, about 250 kilometers. In that, they saw that the disappearance of neutrinos that were made was confirmed by an experiment where we can actually control the neutrinos. We can change their energy, for example, by changing the energy of the machine. We can point in a different direction. They're still not able, however, to measure a particular parameter, this parameter theta 1,3. And that parameter is the one you need if you want to pursue this to, as I mentioned, trying to see whether there is this mirror asymmetry that we think we need to explain why we have a matter-dominated universe. So this was the first one done. And just like I showed you this last Juno experiment, they're now pursuing the next generation neutrino experiments from particle accelerators, and there's two. First one is being done in the US, and it's using the big accelerator at Fermilab near Chicago. And they've done part of this already, and that is they've used man-made neutrinos to go to a mine that exists in Minnesota called the Sudan mine, and saw the neutrinos go. So very much like the Japanese one, the Americans have done a long baseline neutrino experiment from Fermilab. This is just a picture of the detector on the right and how they point the beam from the Fermilab accelerators. Notice that from the picture here, that in order to do this, you actually send the particles through the ground. At the deepest point, it's about 10 kilometers, that's pretty deep, below the surface of the Earth, and no farmers or anyone intermediate or cities see these at all. They're basically down deep under the ground. So you take the accelerator, you point it down at an angle, and it comes back out in a mine in Minnesota that's 735 kilometers away. And with that, they see the events, and they build first a beam and then a detector. So this is the beam, and what happens in the beam here in this picture is you take and make an accelerator that accelerates protons to very high energy, run it into a target, shown here, and then have focusing devices, they're called horns, that manage to shape the electric fields such that the particles are bent toward the direction you want them to go. Then you have, at this point, the kind of particles that are produced in an accelerator, pi mesons, k mesons, protons, neutrons. And you let them go for some distance. In this case, it's 675 meters. In that 675 meters, these particles are unstable. Some of them decay. When they decay, they give neutrinos. And I put up a shield, basically here. The shielding wall gets rid of those. And the only ones that come out the back are neutrinos. These neutrinos are the type muon neutrinos, not like the ones made on the reactor, which were electron neutrinos. So that's the scheme. You can then change the energy of those neutrinos by pointing them slightly differently. If you point the beam slightly differently, the neutrinos that come off, instead of being in a forward direction or in a side direction, you can get different energies. So this is the energy here of the neutrinos. You can see you can set it so that they're peaked at a couple GeV, or 4 GeV, or 8 GeV. This enables you to do what anyone who does experiment wants to do, and it is change the variables in the experiment, changing something to see how it changes the results. So this is something that you clearly couldn't do without a man-made source where you can do these things. So they built this, and they ran it, and it's consistent with what we saw from the other experiments. If the energy of the neutrinos is low enough, they start disappearing. At the higher energies, they don't. This is the line that they would be at if the number produced got to the detector. So the low energy ones disappear. If you then fit this to the formulas that I showed you, you get, again, these parameters of what the mass difference is and what the mixing angles were between those particles. And then you can take that and fit it to what these different neutrinos are. We have the neutrinos that are the muon, or the electron, or the tau neutrino, and then we have the other way of looking at it, the neutrinos that have different masses. So the change in mass that they get is of the order of 2.5 10 to the minus 3. So that's the difference in mass. We know something about the difference in mass, and then this experiment I showed you the first hour, it will tell the mass of the lightest one. This is what the future looks like, just like in Japan, the future experiment being put together for Fermilab is called DUNE, D-U-N-E. It means deep underground neutrino detector. And it's being done in South Dakota, which is a little further away from Fermilab, which makes it more optimum. I think it's 1,300 kilometers away from Fermilab. And again, they make the beam at the accelerator. This is the accelerator. Point them under the ground, and it emerges in a mine that is in South Dakota. This is just some photographs of the accelerator and the facility in South Dakota. This is under construction, and it's something like 5 to 10 years away from being completed. It has, again, a big science program it can do. It can do all these neutrino oscillations, which we need to do. And in particular, there's, I would say, competition and a race and the ability to confirm each other in determining this mass hierarchy. We don't know which neutrino is heavier than which, and hopefully they'll determine that. And these different approaches, one using reactor neutrinos, one using neutrinos from high energy accelerators, will ensure that we get the right answer. Second goal is to actually look for the decay of nucleons. And I mentioned a time ago, but a second ingredient that we believe has to be there in order to explain the asymmetry in the early universe is that the proton itself has to be unstable. It may have a very long lifetime, but it has to be unstable. We already know that the lifetime of a proton is incredibly long. It's 10 to the 35 years, much longer than the life of the universe. But theoretically, it doesn't have to be much shorter than that. It can be longer than that and be okay. So their goal is to see whether the proton might have a lifetime, something like 10 to the 36 years, which would still be very good for helping us explain a matter-dominated universe. They pick a particular decay mode of a possible decay mode of a proton. We don't know if it happens, that they could detect. That's a proton decaying and giving a kaon and an antineutrino. And that's a decay mode that theoretically is a good one to look for. And of course, none of this has ever been seen. Third goal I mentioned before for the reactor experiments is to see a burst of neutrinos that would come from a supernova, from the collapse of a star. So those are three big goals, and they overlap between these experiments, which is what you need. I'll skip this. So the next few slides are just showing you how well they know and can do it, just like I showed you for the Juno experiment that's being put together for reactors. And likewise, this is very carefully being designed to be able to do the physics at the level that we set. So they can do nucleon decay. They go through all the arguments of how good the resolutions have to be, the stability, all the things that I talked about before in order to be able to detect them. And in addition to the detector that's 1,300 kilometers away, they put a detector that's only a kilometer away, I think something like that, or 2 kilometers away. That's shown here, to see the neutrinos that actually come from the machine, the many more of them close, and then you can see how many get to the final detector that was further away. So they have what they call a near detector and a far detector. This experiment then is in a mine that's in North Dakota, and it consists of a type of detector that we call a fine-grained tracking detector made out of high-pressure gas, high-pressure liquid, and it's deep underground in a mine. In order for practical reasons, it's actually being made one at a time, so the first one will be made first, and there'll be a total of 4 of them. The reason they need 4 and not 1 is to gather enough statistics to do the physics that I'm talking about, but otherwise they're identical. Each of them is approximately 10,000 tons of detector, and it's under the ground at about 1,500 meters below the surface. Okay, their first goal is to determine the mass hierarchy, and here I've shown the 2 solutions. So right now, with all the data that I've shown you, we don't know whether the masses of the 3 are this one, the mixes being this, or this one here. One of them is basically in the order of the mass of the dominant identification goes in the same order as the masses of the leptons that go with the neutrinos. That is, the electron is lightest, the electron neutrino is lightest, that's here, muon here, and the tau up here. That's the same order, or they can be reversed. And we don't know which one it is, and that's one of the big goals, both of the reactor experiment and for this experiment. So one of the big goals is to determine the mass hierarchy, and I think I have a plot to show you how well they can do that. Skip a few. Here it is. So this is a picture then of how well they can determine this hierarchy. We call it the normal hierarchy if it's the same order as the masses of the electron, the muon, and the tau, or inverted hierarchy if it's different. And you can see that in order to get a convincing signal, we usually call that 5 sigma statistically, that you can do it here, or here, or here, or here, but we don't know where it is on these plots because we don't know another parameter. So it should be able to tell it as long as the other parameter is in this region, or this region, or this region, or this region, but there's regions in between where you maybe couldn't do it. So can't know until you do this whether they'll be able to tell the hierarchy. And then CP violation. So basically the two go together. Again, once they have this working, and it's probably 5 years from now before it's built, it takes another 3 to 5 years to get the signal that could indicate CP violation or a signal that indicates the mass hierarchy. So all this is kind of the way it'll develop over the next decade or so with ambitious experiments. I have one more thing I want to do, otherwise I'll go. Okay, there's one more detector before we close that I want to show you, and that is the Japanese. This is all new that I showed you at Fermilab, completely new detector, new everything. But what I showed you in Japan was using this big detector that is so impressive with the water and so forth. That's called Super Kamiokande. Now they have just been funded in Japan to make a even more ambitious version, which they call Hyper Kamiokande, and I'll just show you what that is. So it's even a bigger vat of water than the other one. Here's the comparisons up here, maybe too small to read, but for example, the number of tons of liquid in the two detectors are 50 kilotons in the present detector and 250 or 260 kilotons in the new detector, so roughly 5 times bigger. The number of photodetectors is again 4 or 5 times bigger, 40,000 of them, and it covers about the same amount. So basically this gives them a volume that's factor of 5 or so bigger. That of course makes it roughly that much better at seeing whether protons decay or they get that many more neutrino interactions. That has been recently funded in Japan and should start construction shortly. This is just the mountains where it is. It's up in the mountains in the west side of Japan, a mine called Kamioka. And they've basically show the fact that it's more sensitive. The detectors themselves are more sensitive in the new detector. So basically that's now underway. And it will be, again, capable of very accurately studying neutrino oscillations and the parameters of it. And then hopefully something to do with the mass hierarchy, what it is, and whether there's CP violation. And what they're showing here are different results that they would get as a function of energy, observed events, depending on CP violation. So this is the difference in your ability to see different values of the main parameter for CP violation. And again, it has the feature that the unknown can work for you or against you. And if you want a signal that's definitive, then the results have to be above this line that says 5 sigma or at least above 3 sigma. And the actual sensitivity that you have is poor here, good here, and poor here. And since we don't know the parameters, there's a good chance they can measure it, but we don't know for sure. Nature could work against them. So that's it. It also will look, as I said, for proton decay. And it is a sensitivity for proton decay for two different modes. If we ask whether protons decay, they might decay and give a positron and a neutral pion, and they might decay and give a neutrino and a charged kaon. Those are very different modes. And depending on how it decays, and we don't know how it might decay, taking different models of how it decays, one might favor one of those modes compared to the other mode. So searches for these modes or even other modes turn out to be important, and basically that's a big goal of this experiment. So you'll be reading or following the fact that maybe protons aren't stable, or maybe we learn that they are still stable in the next few years. And this is, again, kind of just graphs that show their capability of seeing, in this case, a proton decaying into a neutral pion and a positron, and how they would be detected and what the sensitivity, what their ability is to identify that signal in the picture here. So the proton can decay, and they're able to see it over a fairly wide range. So we expect to be able to tell now whether the proton is stable to another factor of 10 accuracy, and that is to whether it's stable with a lifetime of at least 10 to the 36 years instead of 10 to the 35, which is the present limit. That seems so long that it doesn't matter, but we know roughly how much decay there needs to be in order to explain, have possibilities of how to explain the matter asymmetry in the early universe. And with that, I think I'll end for today. Thank you.